So, what we should have gotten out of the review, along with the first set of questions in the bond energy worksheet, is this. We know that energy is absorbed when a bond is broken. Now, we now know because of those questions that we assign a positive value to that, which makes sense because you have to think we're adding energy to those molecules in order to break their bonds, right? Like we added a third atom to the system with tons of kinetic energy, we let it bump into the other molecule in order to break that bond. Now, if we know that absorbing energy has a positive value, the opposite, absorbing energy has a positive value to represent breaking bonds, then the opposite is also true, that a negative value could be used to represent releasing energy or giving off energy when a bond forms. Okay, so we're going to keep that in our head. Bond breaking, positive value, bond forming, negative value. So in terms of a chemical reaction, though, remember in the reactants, we're always breaking those bonds, right? Like if we're looking at the formation of water here, I have to break the bonds between hydrogens and oxygens so that I have the atoms ready and available to form water. So coming back to positive and negative values, because we're breaking those bonds, we would have a positive value here because energy has to be added in order to break those bonds. On the flip side, for the products, because we're forming new compounds, new molecules, energy is going to be released because we're forming new bonds. So those will always have a negative value. Let's take a look at an example you guys did in the worksheet. This was a pair of reactions. These would be reverse reactions, which means you read the reaction one way, and then if you go backwards, you read the opposite way, right? Okay, so reverse reactions. So this one is phosphorus trifluoride is the technical name, PF3. This is what the Lewis structure looks for PF3. And in this one reaction, we are breaking those bonds there in order to create the individual atoms, phosphorus, and then the 3 fluorines, right? Now, because the bonds are being broken, we notice that there is a positive value here, which means we're adding in energy. The reverse reaction says we have these individual atoms, and then we are combining them. We're forming bonds between them in order to create our PF3 molecule. Since we're forming bonds, we should notice that there's a negative value here, which means energy is coming out, right? Energy is being released. So what if we were to look at the total overall change in energy of a reaction that's not a reverse reaction? What does that do for us then? And at that point, we can start classifying reactions as being either endothermic or exothermic. So endothermic, you guys are probably familiar with. I think you guys mentioned that you've heard of them previously, which is good. Here's your quick review. Endothermic reactions. More energy is being put into the reaction than what comes out of the reaction. So the overall change in energy between the reactants and the products is positive. More energy is being put in kind of sounds like endothermic, right? If more energy is coming out of the reaction than what is being put in, then we call it exothermic. I think you guys have probably heard your teacher say, exo sounds like exit because stuff is coming out, right? The overall change in energy between the reactants and the products is negative. Now, to us, we feel endothermic reactions as being relatively cold. You have to remember, though, that energy is being put in to break those bonds. So that energy could come from thermal energy from our hand. We feel something, the heat from our hand is going into that reaction to help break those bonds apart. And we'll get into that when we talk about cold packs. Exothermic, to us, they feel hot, heat is being given off, and we'll talk about that when we get to the hot packs example. So let's take a look at some examples. Like I said, hot packs, cold packs, that's what started this whole unit. Here's the reaction of those hot packs. We have iron and oxygen. They're reacting to form iron oxide, which, if you guys remember from other classes, iron oxide is just rust. So believe it or not, the hand warmers are just a rust reaction. let's take a closer look at that reaction. Iron is just iron. It's just an atom of iron, so we can't break it apart. It just is there. But when we expose those hand warmers to the air, right, like you open up the package, then you start shaking it, you're exposing it specifically to the oxygen in the air. Now, it takes 494 kilojoules of energy to break this oxygen molecule apart. Once we have those atoms available to be rebonded, we can form this iron oxide molecule. Specifically, it takes 672 kilojoules of energy in order to form that molecule. We notice that there's like the negative sign here in front of our kilojoules of energy needed to form that bond. It's not that like the negative sign is just like a mathematical representation of the fact that we're using energy, okay? It's not like we had a deficit in energy and we magically created the energy in order to form. No, it's like it's being transferred. Remember, it's not just like magically appearing out of nowhere. So, a quick review. We've got iron, it's by itself. It takes 494 kilojoules of energy to break the oxygen molecule here. And then it takes 672 kilojoules of energy to form this. So overall, how do we figure out how much energy is either being released or being taken in? So what you do is a math problem. You add together the energy of the reactants with the energy of the products. So we would add together 494 plus negative 672. The resulting sign is going to tell us if it's endothermic or exothermic, and that comes back to endothermic being overall positive, exothermic being overall negative. So when we add them together, we get a resulting negative 178. The negative sign tells us that energy is being released, and so the overall reaction is exothermic. Now, does that actually make sense? It should, right? Because we said exothermic should feel kind of hot, should feel warm, because energy is being released. That would make sense. Hot packs, hot pockets, hot packs, they feel hot, right? So that makes sense. Now let's take a look at the opposite. We were looking at cold packs. Here's a reaction, not necessarily for cold packs, but it is an example of a reaction that is endothermic. We have some pretty complex molecules here. Take a look at what is on the reactant side. I'm not even going to bother listing out the names of those because it doesn't really matter. Just know that it takes 1,425 kilojoules of energy in order to break the bonds that make up those molecules. On the flip side, it only takes 962 kilojoules of energy in order to form those bonds. So overall, what is the energy change, and is that reaction going to be exothermic or endothermic? Well, if we add together 1,425 plus negative 962, we get a resulting positive 463 kilojoules of energy. That positive sign lets us know that there's more energy being taken in than being released, and so the reaction is endothermic. To us, it's going to feel relatively cold. Now, what's interesting to note here is that the energy that's being released from forming the bonds, that energy is automatically reused and recycled to break the next round of bonds in the reactants. So it's kind of cool to think about that. Again, this is a reaction that represents the cold packs. So we have our example of an exothermic, the hot packs, endothermic, the cold packs. So remember back to your initial models. Maybe you guys labeled them the right way, maybe not. Okay, so here's what your guys' job is for the remainder of this lesson. If you go back to your bond energy worksheet, you should already have these first questions answered, and you are working on these last ones here. There are 3 examples of reactions. For each one, we've given you information about how much energy it takes to break the bonds of the reactants and how much energy it takes to form the bonds of the products. Your job is to determine if those reactions are endothermic or exothermic. The way you do that, first you'll show your math. Very simple, just like what I did in these examples here. Remember, you're adding together the energies of the reactants and the products. Once you have your final number there, highlight or bold or select Your answer that fills in the blank, the above reaction is endothermic or exothermic. And then just describe how did you know that based off of your math. So 3 problems to tackle there. And once you're done, then you are good to go for the afternoon time where we're going to take another look at these guys and practice some more. So if you have any problems, let me know. Email me. I'm here to support you. Remember that I do have office hours, 2:40 to 3:10 on Monday if you happen to work on this ahead of time. Otherwise, we'll see you guys on Tuesday.